Without further ado, we will introduce our moderator for today, Dr. Emily Cole. Emily is the Associate Director for Research Relations at the Cockrell School of Engineering at UT Austin. Take it away, Emily.
Thank you, Javier. Hello and welcome to our newest webinar in our Tech Talk series. Today's event will focus on carbon dioxide capture with ionic liquids. If you are new to our seminar series, the format will first include a presentation by our speaker, followed by a moderated Q&A session where we welcome questions from the audience. We ask our audience members to please type your questions in the Q&A box throughout the event and we'll answer them immediately after the presentation. Without further ado, it's my pleasure to welcome today's speaker, Professor Joan Brennecke. Dr. Brennecke is the Cockrell Family Chair, number 16 in Engineering in the McKetta Department of Chemical Engineering here at the University of Texas at Austin. She joined UT Austin in 2017, following an academic career at the University of Notre Dame. She currently serves as the Deputy Director of one of NSF's research centers, the Center for Innovative and Strategic Transformation of Alkane Resources, or CSTAR. Her research interests are primarily in the development of less environmentally harmful solvents, including supercritical fluids and ionic liquids, for applications such as CO2 capture. In developing these solvents, the group's primary interests are in the measurement and modeling of thermodynamics, thermophysical properties, phase behavior, and separations. Dr. Brennecke is a member of the National Academy of Engineering and has received numerous awards from the American Chemical Society, the American Institute of Chemical Engineers, the U.S. Department of Energy, and others. She has published more than 200 research papers, garnering over 20,000 citations, and has served as editor-in-chief of the Journal of Chemical and Engineering Data since 2010. I'll now hand it over to Joan for her talk titled CO2 Captured with Ionic Liquids.
Thank you very much, Emily. Let me share my screen. All right, I think we should be ready to get started. I want to thank everyone for coming and enjoy having the opportunity to talk with you about some of the work that we've been doing over essentially the last 15 or 20 years, looking at the development of a class of materials called ionic liquids for a variety of separation processes. And today, of course, I'll be talking about CO2 capture. And so the things that I would like to cover today is just to give a little motivation and background for the work that we're doing, and then talk about some of the specifics of using ionic liquids and designing and developing ionic liquids for CO2 capture applications, talking about the chemical complexation between ionic liquids and CO2. I'll also tell you about some materials we've developed that we call phase change ionic liquids, some work we've done with encapsulating them, and finally to talk a little bit about current directions, areas where we're moving with this work at the moment, before summarizing up. So really, as motivation, we all know that the use of fossil fuels has continued to increase, actually pretty dramatically, as shown here in the data from the International Energy Agency. The three bottom ones are coal, oil, and natural gas. And while the fraction of our total world energy use is decreasing, it's gone down from about 85% to almost 80% in recent years, but the total amount of natural gas, oil, and coal does continue to increase. And along with that increasing use of fossil fuels, is a dramatic increase in the amount of CO2 in the atmosphere. And so this is the data that I'm sure many of you have seen from the Mauna Loa Observatory, where we've gone now over 400 parts per million of CO2 in the atmosphere. And this has various implications for global climate change. So we might want to reduce CO2 emissions, and of course there's many ways of doing this, and I just list some of them here. One of course is reforestation, afforestation, planting new forests to uptake the CO2. Another is a much more vigorous transition to renewables, although I would argue that there has been tremendous efforts and achievements in this transition. It's just a very large and formidable task. We can encourage energy conservation, get us all to ride our bicycles to work instead of taking our cars and that sort of thing. We've obviously done a lot of energy conservation in the past year because of COVID. I haven't been on a plane in more than a year, and that's quite different than the previous years. We can work to improve energy efficiency. And, this is for anything from, mileage, fuel efficiency in our cars, to appliances and so on. We can also reduce CO2 emissions by fuel switching from coal and oil to natural gas. And the reason this, of course, is that the energy content per carbon atom is significantly greater in natural gas than it is in coal. But then another possibility in trying to reduce the amount of CO2 that we put into the atmosphere is to actually capture it and either sequester it or do something else with it rather than letting it go into our atmospheric environment. And so that's what I'd like to talk about today. Point sources like power plants, whether they're coal-fired power plants, natural gas-fired power plants, are really excellent targets because the concentration of CO2 coming out of the flue gas is obviously much greater than it is in the atmosphere. The challenge here is that we have technology that we can use to capture CO2. We use it in submarines and many other places, but the conventional technology is based on primarily on aqueous amine solutions. And the problem there is that if these were put on point sources like power plants, they really require a significant amount of energy to run the capture process. The estimates for things like aqueous monoethanol amine solutions are about 28% parasitic energy load, which means if you had a 500 megawatt power plant and you installed CO2 capture with that technology, you'd be down well below 400 megawatts as the real output from that plant. So what we really need are lower energy and lower cost processes for removing CO2 from post-combustion flue gas. There's other issues associated with aqueous amine solutions. They are corrosive and various side reactions. They degrade even at relatively low temperatures. Those types of processes would run something like what's shown here, in that we've got a power plant and we've got exhaust from the power plant. It's at essentially atmospheric pressure. If it's a coal-fired power plant, the concentration may be about 12% CO2. If it's a natural gas combined cycle power plant, it may only be about 5% CO2. But we would take that mixture, and the major component, there's water in it, of course, but the other major component is nitrogen. And we would contact it with some sort of absorbent like the aqueous amine solutions. And those solutions would pick up the CO2, so that coming out of the bottom of that scrubber column would be our absorbent loaded with CO2, and that would allow the cleaned exhaust gas to go out the top of the column. But of course, we want to reuse our absorbent, so we need to run to a regeneration column where we would drive the CO2 off and reuse our absorbent. And so this would be a kind of a typical process. And the reason why it requires a lot of energy is primarily, or a big part, is the energy needed for the regeneration. So you have to supply the energy to uncomplex the CO2 from the absorbent. And with the aqueous amine solutions, along with this, you end up evaporating a fair amount of water. And the enthalpy of vaporization of water is quite a high number. So all these combinations of things mean that the amount of energy required for the process is quite high. So many people are working on a wide variety of alternatives to this. And oh, I should mention here that a few of these over here, Selexol and Rectisol, these are not aqueous amines, but they're more suitable for higher partial pressures of CO2 separations versus the aqueous amines like those offered by Fluor, the Econoamine, FG+, and other companies. Some of the alternatives, there's a lot of people working on solids that would be adsorbents. So these are things like MOFs, metal organic frameworks, various different types of carbonaceous materials. There's also a lot of work in developing membranes for doing CO2 separations. And then there's really a class of solvents that people have started to call water-lean solvents. And one of the major ones of these are, in fact, the ionic liquids that I'll talk about today. So, what exactly are ionic liquids? Well, ionic liquid is a name given to salts that have low melting points. The definition that's frequently used is a pure salt that has a melting point below 100 degrees centigrade. Without any water added, these can be liquid at room temperature. There's a picture in there, and also I'm holding up a sample of an ionic liquid that I actually made myself about 20 years ago. And one of the interesting things about them is that because they are salts, they have very strong coulombic forces between the cation and the anion. And as a result, they have basically infinitesimally small vapor pressures. So they're essentially non-volatile. And that's an advantage for doing gas separations, because then there would be no slip or no contamination of your purified gas stream with the solvent that you're using for the separation. As I suggested before, we can use these without any added water. So we can use them essentially anhydrous. They tend to have a very good thermal stability. They don't boil, obviously, because they don't have any vapor pressure. So you can just keep heating them up and they'll still be liquids until eventually they start having some thermal decomposition. But in many cases, that's 300 or 400 degrees centigrade. The other interesting thing about ionic liquids is that we can make these low melting salts out of a wide variety of different cations and anions. And I just show a few of them here down at the bottom of the slide. There's tetraalkyl ammoniums, tetraalkyl phosphoniums, imidazoliums, just all kinds of different possible cations. The anions can be simple things like halides, but also much more complicated things like tetrafluoride or bis-trifluoromethylsulfonamides, some of these other ones that we have shown here. In general, I tell people that ionic liquids are not like simple alkali salts like sodium chloride, which of course has a very high melting point. They tend to be more organic-y, and the charge is distributed among, more across the cation and the anion, which weakens the interactions a little bit so that they that reduces the melting point. But more importantly, the asymmetry in these cations and anions make it difficult for them to pack, and so this also lowers the melting point. But we have a great variety of design space in which we can use to make ionic liquids for a wide variety of different applications. So we first found out that CO2 was pretty soluble in an ionic liquid more than 20 years ago. At that time, most people were using ionic liquids as solvents for reactions and saying that that was environmentally beneficial because they weren't using a volatile organic solvent for the reaction. But then they still needed to get the product out of the mixture at the end, and they would resort to using something like diethyl ether, which of course is VOC. And so at the time I was doing work on supercritical CO2, and so we decided to just try to extract a relatively low volatility product out of an ionic liquid with supercritical CO2. And to do that, we needed to look at the phase behavior. And this is what we found. We couldn't detect any of the ionic liquid in the CO2 phase. That's the blue line over on the right. But we could find actually a fair amount of CO2 dissolving in the liquid phase. Now, the pressures at which we were doing were quite high, right, because we were doing supercritical CO2 extraction. But nonetheless, that's made us think about what is driving the solubility of CO2 and other gases in these liquid salts. And so here we started looking at a little bit lower pressures and measuring the solubility of CO2. And here is an imidazolium bistriplylamide ionic liquid. In fact, this is exactly the one that was in the vial that I was holding up a minute or so ago. And when we did these measurements, we found, of course, that the solubility of the CO2 in the ionic liquid increased with increasing pressure, which is what we would expect, and that it decreased with increasing temperature, which indicates that there's attractive interactions between the ionic liquid and the CO2. So this is an important observation because it means that we could absorb CO2 at a lower temperature and then desorb it by raising the temperature. And we saw similar trends for CO2 solubility in a wide variety of different types of ionic liquids. Now here's where we then said, well, what's the solubility of CO2 in ionic liquid compared to the solubility of, say, nitrogen? And so this is a slightly different ionic liquid. The same anion, but instead of a imidazolium cation, I'm using a pyridinium cation. These measurements, you can see the CO2 is the red circles, which is relatively high solubility compared to something like nitrogen or oxygen, which is down at the bottom, very low solubility. And so this suggested to us that we could have good selectivity of CO2 over nitrogen. Even with here, all we're doing is just physical dissolution of these gases in the liquid. There's no chemical reaction or anything taking place. But when we did the analysis, we found that we really needed to have a much higher capacity for the CO2 in the ionic liquid if we were going to use it for something like post-combustion flue gas, where the partial pressure of CO2 is very low. The physical dissolution gives us a low enthalpy absorption, which means that you don't have to add much heat to regenerate it to drive the CO2 off. But the low capacity meant we'd have to have very large ionic liquid circulation rates, and that we really needed to increase this capacity. So the place to go is, in fact, to try to incorporate reversible chemical complexation between the ionic liquid and the CO2. And we want this complexation to be strong enough to increase the capacity so that we could decrease the ionic liquid circulation rates, but weak enough to keep the regeneration energies down. And we were guided by a paper that appeared in the literature from Jim Davis's group, which is shown here. And what he had done was to tether an amine onto an imidazolium cation, and that's what's shown at the top. And that amine, like regular aqueous amines that are not charged, that amine then reacts with CO2, so it picks up the CO2. But then what also happens is that another amine comes by and deprotonates that. So there's actually two steps in the reaction, and this is consistent with what happens with most regular aqueous amine solutions, is that you need two amines, two of the bases, to pick up one CO2. And this is what they observed they actually just bubbled CO2 through their liquid mixture, and with time got up to about 1/2 mole of CO2 per mole of the ionic liquid. They also noted that when they did that, the viscosity really increased, which could be a big issue as we move forward to thinking about more commercial applications. One of my colleagues, this was back when I was at the University of Notre Dame, they did some density functional theory calculations. These are quantum calculations, gas phase, just to get an idea of the energetics of the reaction of the CO2, both of those two steps that I showed you in the previous slide, relative to the things we know, the molecular amines, the like monoethanol amine. So the line in the middle is the monoethanol amine, and so the first step is the addition of the CO2, and the second step is the deprotonation by the second amine. And the top line is comparable to what Jim Davis's group had done, which is tethering an amine onto the cation. And what was found is that the first step is pretty similar in energy. So you're going to add the CO2. It's pretty similar in energy to what happens in aqueous amines, traditional aqueous amines. But the second step, the deprotonation, is very much downhill relative to the aqueous amines, which means it's really favorable. It's definitely going to happen. So you're definitely going to get that deprotonation. But what they also found was if we were to tether the amine on the anion, energetics of the first step, the CO2 addition, is still good, but the deprotonation is very uphill. So the prediction was that if we did this with ionic liquid where the amine was on the anion, that second step wouldn't happen. And the reason is that it requires the formation of a dianion, which is energetically not favorable. So that's what we did. We made some ionic liquids with actually amino acids. So these have a phosphonium cation, but an amino acid moiety as the anion. And so I'm showing you here a methionate and a prolinate ionic liquid uptake. And so it's moles of CO2 per mole of ionic liquid. And you can see for these guys that even at really low partial pressures, we get a lot of CO2, and in fact, significantly more than half of a mole. So this confirmed the prediction that if we put the amine on the anion, we could essentially double the uptake per mole of amine. Unfortunately, we also observed a very large increase in viscosity upon reaction with CO2. In fact, that is shown here in this graph, which should frighten anybody if you look at the scale. It's a log scale on the left, and these are viscosities in centipoise, where water is 1 centipoise, and 100 is starting to be kind of gooey. And what you'll notice if you look, for instance, at the lysonate, the green ones, all right, without the CO2, it's starting out a couple hundred centipoise at 40 degrees C where we might want to use it. But once we react it up with CO2, the viscosity goes up by 2 orders of magnitude. And so that's basically, you turn it upside down and it does not flow in the vial. So that's very bad. But we also noticed that the prolinate increased in viscosity. This is from the yellow to the red. It increased in viscosity, but not nearly as much as the others. And so the question is why is that so? And you can see that the prolinate is the guy over here on the right, which has the ringed structure, the only one that has the ring structure. And so another one of my colleagues, Ed McGinn, they did some molecular simulations and identified the cause of the viscosity increase was the formation of a hydrogen bonding network between the reacted up one with an unreacted one. And so the key to keeping the viscosity from increasing was to get rid of the opportunities for that hydrogen bonding. And the hypothesis was that the prolinate was better because it was sterically hindered in forming these hydrogen bonds. So this is where we invented a class of ionic liquids that that include what we call aprotic heterocyclic anions, or AHA ionic liquids. And so they are things like peroxides and pyrazolides that are shown here. And so what I'm plotting is, once again, moles of CO2 per mole of ionic liquid. Once again, at low partial pressures of CO2, and you can see we get significant uptake. It goes up to near 1 mole of CO2 per mole of ionic liquid. But the most important part was that the viscosities did not increase when we reacted them up with CO2. You can see virtually no increase in viscosity. And so that was a really significant advance in being able to potentially use these as liquids in like an absorber type. I mentioned the perolides, pyrazolides, there's imidazolides, triazolides, all these different types of possibilities of these azolides that we can use. What's exciting is that we can adjust the enthalpy of reaction between the CO2 and the ionic liquid by our choice of perolide, pyrazolide, so on, but also by putting electron donating or withdrawing groups on these base structures. And we can really tune that enthalpy reaction to be what we want it to be. And so here's an example of where we've got a bunch of different ILs. They've all got the same tetraalkylphosphonium cation, but different anions that have been adjusted in this way. And you can see with moles of CO2 per mole of IL as a function of pressure, of CO2 partial pressure, some of them pick up an awful lot at extremely low partial pressures, and others increase more gradually. So the ones that are very steep here have large negative enthalpies of reaction, values up to about minus 50 something. And then the weaker ones are down as low as minus 30 something. And so this means we can tune this enthalpy of reaction. Where we've got very low partial pressures of the CO2 in our mixture that we're trying to separate, we would want to use the stronger binding ones so you can have higher capacity. If you've got somewhat higher partial pressures, you might want to use some of those slightly less strong binding. The next thing I wanted to mention is something that we discovered rather, well, clearly by accident, all right? And it's what we call phase change ionic liquids. This material is tetraethyl phosphonium benzimidazolide, so it's the same type of material, but with much shorter alkyl chains on the cation. And it turns out that the material would not officially be classified as an ionic liquid because it has a melting point of 166 centigrade. But what I'm showing you here are pictures all at 70 degrees centigrade, so almost 100 degrees below the melting point of the pure material. And you can see that when we start adding a little bit of CO2, it starts looking liquid. And by the time we've got 1/10 of a bar of CO2, it's completely liquid, 100 degrees below the melting point of the unreacted material. So what this says is that the material reacted with CO2 has a much lower melting point than the original material that isn't reacted with CO2. And that's actually very useful because this can dramatically decrease the amount of energy that's required for the regeneration process. And that's because I told you already that a lot of the energy for the process is because we have to add heat back in the regenerator to unreact the CO2. So say we're doing an ionic liquid where the enthalpy of reaction is about 50 kilojoules per mole. Normally that's what we would have to add back, is 50 kilojoules per mole of CO2. But in the phase change ionic liquid, in the regenerator, what's going to happen is you're going to have that liquid that's going to be then releasing the CO2 and going back to a solid. And when the material goes from liquid to solid, it gives off heat. And so how much heat? Well, it's the heat of enthalpy of fusion. So it turns out that this material has enthalpy of fusion about 20 kilojoules per mole. So 20 kilojoules per mole of the 50 is being supplied by the phase change from a liquid back to a solid of the ionic liquid. So that the net amount of heat that you have to add is not 50, it's only 30, right? And there's benefits in the absorber also. In the absorber where it reacts with CO2, you have to remove heat from the absorber. It heats up. And so in this case, then you have to remove less heat from the absorber. The isotherms for the uptake of the CO2 as a function of partial pressure actually are shown here. And they're really steep. And if you do the thermodynamic model, there's a good reason for that. We can predict that they should be this way. And that's very nice because this means that you can absorb at a particular partial pressure, and then all you have to do is reduce the pressure a little bit in order to desorb it. And you can go from almost, full uptake down to almost nothing with a relatively small pressure swing between the absorber and the regeneration. This work in collaboration with some colleagues at a company, Matrix. They did the sort of pilot plant demonstration as well as the techno-economic analysis. And for this particular material that I've been showing you, they found that the overall process energy requirements were reduced from the 28% or so that I showed you or mentioned earlier for the conventional aqueous amines, down to about 23%, which would be about a 4 cent per kilowatt hour increase in the cost of electricity, and the equivalent amount number for the cost in tons of CO2 avoided. So these are starting to be somewhat attractive, both from an energy standpoint and from a cost standpoint relative to conventional amines. More recently, one of the things we've done is to encapsulate the ionic liquids and the phase change ionic liquids in little shells. Now, the justification for this is, or the motivation for this, is that we still have viscosities that are significantly greater than aqueous solutions. All right, so our viscosities at operating conditions might be 100 times that of water. When you do that, then you have to worry very much about the contact between the gas mixture and the ionic liquid, and you're really going to have mass transfer limitations because of that high viscosity. So the idea here is to increase that mass transfer between the gas and the ionic liquid by dramatically increasing the contact area between those two phases. And this would decrease the column size and decrease capital costs. So just as an example over here on the right, this is the surface area per unit of absorber volume. And so even if you use some of the really cool structured packings like those developed and tested by Jim Fair many years ago when I was an undergraduate here at the University of Texas, you still are pretty limited on that surface area to volume. Whereas if we could encapsulate the ionic liquid in little shells, then we could increase that contact area by probably 2 orders of magnitude, depending on what is the diameter of those capsules. So in doing this, we worked with some colleagues at Lawrence Livermore National Lab, Josh Stolaroff and his group, and they encapsulated our ionic liquids in some cross-linked silicone shells, which found ones that were chemically compatible with the ionic liquids. And they actually made these little shells, encapsulated ionic liquids and phase change ionic liquids in a microfluidic device. This is just to show you that this actually works, because then when you have these little capsules, maybe a ½ millimeter in diameter or something like that, you can do the contact between the gas and the liquid phase in a fluidized bed, and that's just, well, that's slug flow in a fluidized bed, but showed that we can fluidize and do very effective capture of the CO2 with the encapsulated ionic liquids. So the last thing I wanted to mention is kind of some of the directions we're headed in at the moment. We're very, very interested in developing ionic liquids for a wide variety of CO2 separation applications. The ionic liquid that's going to work best for one application will not be the same one that would be best for another, and that's because of chain differences in concentrations and partial pressures and temperatures and so on. And so we're very interested in working with industrial partners to design these ILs for these different applications. And to facilitate this, we're working with Professor Michael Baldea and Mark Stodhair in a project that is funded through the UT Energy Institute, Fueling a Sustainable Energy Transition, in which we're trying to do combined IL and process design. So what this means is that we can have feed specifications, our CO2 separation targets, but then we need to have models for the ionic liquid properties, the viscosities, the heat capacities, the CO2 capacities. And to help develop these models, we're working on the development of some machine learning tools, using some machine learning tools to develop those models. We can then specify our objective functions and various constraints, whether we're trying to minimize energy, cost, or both, size, for instance, so that we can get the combined best process and the best IL for those for that CO2 capture process. Another thing that we're interested in doing is combined CO2 capture and conversion. This is a slide from a colleague of mine at Pacific Northwest National Lab, with the idea that CO2 in, for instance, flue gas is at a certain energy level, but once we've reacted it with the ionic liquid, we've actually activated it, reduced its energy, but activated it. We would normally desorb it, which increases the energy. Compressing it would, for putting in a pipeline, would further increase the energy. And then you could use it for something. But if we were to skip the compression and the regeneration, that might make a lot more sense to use this activated version of the CO2 that's reacted with the ionic liquid to then convert it to saleable products. So in making commercial products could definitely then improve the economics of the CO2 capture. Now, the scale of this doesn't match. We couldn't be doing this capture and conversion for all of the CO2. We have much more CO2 than we have products made out of carbon that we would want. But this might be a help to move us in the direction where CO2 capture could make sense. So in summary, what I've talked with you about today is that ionic liquids are these really interesting tunable solvents with potential for actually a lot of applications, but including CO2 capture. The things we've been able to do is to increase the molar capacity and get rid of this viscosity problem. We can tune this enthalpy of reaction so we can make ILs for a variety of different applications. I also showed you the phase change materials that can further reduce the energy consumption, and the idea of being able to get rid of some of these mass transfer resistances with the encapsulation idea. I think there's many opportunities for other CO2 applications with with ionic liquids, and the potential for capture and conversion. With that, I have a recent picture of my group. A lot of the work that I talked about was done by former group members, but I put some of their pictures up. A lot of this work has been funded by the Department of Energy, especially the National Energy Technology Laboratory and ARPA-E, so I thank them. And if you're interested in talking with us about CO2 capture for some of your applications, that's me, and that's my email address. That's the best place to get a hold of me. And I'd be happy to then try to answer any questions.
Thank you, Joan. That was a great, enlivening talk. We actually do have a lot of questions coming in from the audience, so I'll start to try to go through those here. Our first question is a very good question here about where are we in terms of implementation of these new carbon capture technologies. So are any of these ionic liquid technologies now, in pilot scale or operational scale?
With the ionic liquids?
Yes.
I think the biggest that I'm aware of is sort of the small pilot scale. Of some of the things where we've done work. Some of the other folks out at PNNL have done similar work where we're talking about the amounts of ionic liquid that we've needed was 10 gallons, but not a really huge pilot plant. I'd say that's about where we are.
Okay, so where do you see it kind of going then in the future? Are you seeing this going to be commercially deployed maybe 5-10 years?
Oh, I think it could be commercially deployed in 5-10 years. But as with all CO2 capture technologies, the financial incentive is not really there except in the Q35 credit. So that's why we're looking at things like the capture and conversion, where you could have some additional revenue streams that could make this more financially attractive.
That makes sense. And I think we do have some questions around costs, so we'll get to those as well. But that kind of ties into, well, once you've captured the CO2, what do you do with it? What can you do with it? So one question we have from the audience is on the regeneration side, after you've captured it by the ionic liquid, how do you release it? Is that gas form? Is the next step to go to underground injection, or are you trying to utilize it? What are some ways to use the CO2 once you've captured it?
Right. So the big potential place where we can put CO2 is, of course, sequestration, underground storage, right? And so that's why you would need pressurized CO2. And yes, it is desorbed as gaseous CO2. And so then you could compress it to higher pressures and inject it into geological formations. Of course, there is need for CO2 for enhanced oil recovery, so it can be used for enhanced oil recovery. Then the other one, which I mentioned at the end, which was the potential of doing conversion, with the caveat that if we made all of the organic chemicals in the world out of CO2, it would only put a couple percent dent in the amount, all of the CO2 that we release into the atmosphere currently. So it would certainly need to be a combination of those things.
That's great. And it looks like we have in our audience members a lot of folks from the natural gas industry. So they have some interesting questions. One, have you looked at using ionic liquids for separating CO2 from natural gas to get the CO2 content below the 2% that's required for pipeline transport?
Yes. We've certainly done a lot of measurements of the solubility of methane and CO2, of course, in the various different ionic liquids. And there's many where the selectivity looks quite good. We haven't had any big projects on CO2 natural gas. We've got one that we're starting up actually to do undersea separation, so high pressure separation of CO2 from natural gas. But yeah, I think that is a potentially great application for the ionic liquids.
Yeah, it sounds like there could be some good opportunities there to work on that kind of idea together. And there's another question that's kind of similar. So could the ionic liquids be used for natural gas sweetening? And by natural gas sweetening, for our audience members who may not know, that's the removal of hydrogen sulfide. So would that be an application?
Well, okay, so there's natural gas sweetening usually refers to both the CO2 and the hydrogen sulfide and the H2S. Certainly we can use it for the CO2. These particular ionic liquids that we've designed, containing the amines for CO2 capture, actually are not real happy with H2S. It turns out, though, that H2S is extremely soluble in a lot of ionic liquids where it's just physical dissolution, so where you're preventing any unwanted reactions from taking place. So it would be a different ionic liquid to remove the H2S than to remove the CO2, but that can also be done, and there are measurements, and we've made measurements of H2S solubilities in ionic liquids. So I would envision a sort of a two-step process, one where you use one ionic liquid to get the H2S out, and then another process or another IL to remove the CO2.
Would they be combined in kind of one process step, or would you see that as kind of two process steps?
I kind of see it as two process steps, but I guess there is possibilities of where you could combine it in a single unit, right? As long as you were, keeping the, well, I don't know. I haven't thought about that enough.
Yeah, but there's opportunities there. Here's another interesting question about the pipelines. So have you found any ionic liquids that can be injected into a CO2 pipeline to act similar to a DRA in other liquid services?
I haven't thought about that. But yeah, that'd be something I'd like to talk with them about.
Yeah, that sounds like a pretty interesting idea. I had not seen that before either. And then another question, it kind of gets to, we're talking a lot about CO2 today, but ionic liquids have been around a while, and there's been, so much innovation coming from your group and others to develop new methods and new ionic liquids. So what are other uses of ionic liquids currently commercially out in the field?
I mean, it spans the gamut, right? I mean, there's so many different applications. The first interest, and there still is interest, is using a lot of interest in using ionic liquids as electrolytes, because you can replace water, which has its limitations because you split water, right? So just use the ionic liquid itself, and then it's not volatile, so you don't have to worry about the flammability of the ethylene carbonate and propylene carbonate like we have in batteries, right? The challenge is always getting the conductivity to be high enough, right? But boy, there's a lot of electrochemical work, right? We've done work on electroplating of chromium. There's all kinds of electrochemical work in ionic liquids. Using them in dye-sensitized solar cells, okay? The original work was actually using them as alkylation catalysts, right? So as a liquid alkylation catalyst, and that's commercial. There's I'm getting distracted. So, there's commercially in Malaysia using an ionic liquid to remove mercury from natural gas. Apparently they have relatively high levels of mercury. People have used them as pressurization fluids, right? Because they're pretty incompressible. So you can just go on. And there's a nice book that came out last year that Mark Shiflett put together on commercial applications of ionic liquids. I think it's from Springer, which details a lot of these different applications.
Okay, thank you. That's great. And then kind of going back again to the other components of flue gas, we're talking a lot about CO2 today, but your flue gas components, you have your SOx, your NOx, water. What happens to them when you're capturing CO2? Can you capture these other components that you would like to, or what do you envision there?
Right. So like other amines, they're not very happy with SOx. You would still need to, you'd still need to have your SO2 scrubber ahead of your CO2 capture. Some of them are not as bad with NOx. So there's the possibility that if you have, low NOx burners and that sort of thing, that you could run that and pick up some of the NOx with CO2 if you wanted to do that. The main issue is water, because water is a major component of flue gas, and the ionic liquids are salts. They like water. Even the hydrophobic ionic liquids still pick up water. All right. So it turns out that you do get some additional chemistry going on, which we have investigated. It is reversible chemistry, so you can, have the parallel reactions with the water and with the normal CO2 uptake, and both of which are reversible. So it is additional consideration, the water. You're going to want to have things that are a little bit hydrophobic so you don't pick up a whole lot of water. And the tetraalkyl phosphoniums that I was talking about today fit that bill.
So it sounds like, again, going back to the system design along with the chemistry design to get the optimal kind of composition or process that you need for a specific flue gas. That's good. And this kind of goes back, I know you've done work in this field, and we talked about a little bit today, but have you considered using the captured CO2 in a CO2 electrolyzer? And then using, of course, excess renewable energy so that you basically have a way to convert that CO2 into something value added, but not producing any more CO2.
Yeah, so the work we've started to do so far is, thermal catalytic conversion of the CO2, but the obvious other one is electrochemical conversion of the CO2. I have a couple papers on electrochemical conversion of CO2, but when we tried to do it with our initial work, doing it with the these AHA ionic liquids, didn't really show a whole lot of advantages. So that's an area where we would need a lot more work.
That's good. Yeah, I think the thermal approaches, though, sound very interesting for kind of another way of going after it. So I think we are at the top of the hour. So thank you again, Joan, for this great talk and the Q&A session. I would like to thank the audience also again for a very engaging discussion. We've tried to get to a lot of your questions, but we had very many today. So as mentioned before, a link will be sent for the live event in the next few days. If you would like to connect with Dr. Brennecke, please do not hesitate to reach out either to our research relations team or directly to Joan. We thank you for your time today, and now I'll hand it over to Keneva Smith.
Thank you so much, Dr. Brennecke, and thank you all for attending today. We hope the conversation was valuable. If you would like to learn more about future webinars or to hear more about hot topics that are changing the industry, just such as this, please be sure to follow us on our social media channels. As you've heard today, lifelong learning and technical adaptability is fundamental in preparing individuals to remain competitive in today's environment. If you enjoyed our fantastic speaker and would like to learn more about partnering with the university on research opportunities, please email the Research Relations Office to initiate a discovery discussion. The Research Relations team partners with companies from around the world to solve some of the world's biggest problems in energy, water, transportation, and many more. The Office of Research Relations works to facilitate and derive high value from research collaborations between your companies and UT's researchers, and they would love to work with you today. Along with the Research Relations team, we also want to thank the 2 additional units of the Cockrell School of Engineering that helped put this wonderful program together. First is the Texas Engineering Executive Education Program, who works to reskill and upskill companies' current workforce, either through their master's degree programs, graduate certificates, or short courses. So if you have a need around STEM education or training, make sure to contact our department to learn more. Next is our PTEX department, or the Petroleum Extension of Texas. This department has been around for over 75 years, serving the oil and gas professionals with skills trainings, either through e-learning, publications, online or in-person training. We have the training to meet your energy needs. All 3 units who are here to serve you and your company through education, training, and research. So feel free to contact us at any time, and we would love to collaborate on helping you reach your company's full potential. If you would like to provide feedback on today's webinar or to learn more about receiving CEUs from today's presentation, make sure you complete the evaluation survey in the chat or in your email following this presentation. Once again, we'd like to thank you for joining us today. We hope you have a great weekend and hook 'em horns.